Hello everyone, myself Srivasudeval. I am from first year EC department in SVC College Bangalore. Today we have to discuss about the topic conduction of heat related to mathematics. First we have known about the mathematics of heat conductions. This presentation delves into the mathematical foundations of heat conductions, exploring the interplay between the physics and mathematics. Next, we move on to the understanding the heat equations. There are two steps, the foundations and key components. In foundation, the heat equations is a fundamental partial differential equation describing the distribution of heat over time. In key components, it relates that the rate of change of temperature to the second derivative of temperature representing heat diffusions. Let's move on to the odd order partial differential equation. They have two types, unusual behavior and unique solutions. Odd order partial differential equations exhibit the different properties compared to their even order counterparts in unusual behavior. In the unique solutions, in these equations can lead to unique solutions with characteristics not observed in standard heat transformer modules. Next, we move on to the applications in the real world. It is used in engineering and meteorology. In engineering, the heat equations helps to engineers design efficient heat exchanging and optimizing the thermal systems. In meteorology, meteorologists use the equations to understand and predict weather the pattern including heat waves and front formations. Next, we move on to the numerical techniques for solving. They have two methods, finite difference method and finite element method. This technique in finite difference method, this technique discretizes the problems into the grid or used finite difference to approximate derivative. In finite element method, the problem is broken down into the smaller element and approximate solutions are combined to form the initial final result. Let's move on to the thermal diffusivity. First, we know about definition of thermal diffusivity. The thermal diffusivity is a material proper by representing how the quickly heat diffuses through substances. Next, impact on heat transfer. Material with higher diffusivity transfer heat faster, influencing the rate of heat conductions. Next, we move on to the boundary conduction. They have three boundary conditions. The first one, the fixed temperature. In this conduction specifies a constant temperature at the boundary, like an object in contact with a heat source. In insulated boundary, no heat is allowed to flow across this boundary, representing an insulated surface or a vacuum. Mixed boundary. In these conditions, combines the element of fixed temperature and insulated boundary, reflecting a real world scenarios. And next we move on to the connections to other field. This, there are two connections, the quantum mechanics and finance. In quantum mechanics, the heat equations has applications in transformer mechanism, particularly in the study of heat diffusion in quantum systems. In finance, the equations can model price fluctuations and option pricing in financial markets. Let's move on to the geometric applications. They have two geometric applications. First one is shape optimization and heat distribution analysis. In shape optimization, the heat equations can be used to find the optimal shape of for object that need to efficiently transfer heat. In heat distribution analysis, it helps analyzes the heat distribution within irregular shape object leading to improved design and performance. Next, we move on to the concluding remarks and future directions. First, the key insights. The heat equations provide a powerful mathematical framework for understanding and predicting heat transfer. Second, open questions. Further research is needed to exploring the behavior of the heat equations in more complex system and conditions. Thank you. Thank you, Manada.